Hi everyone, today a video in the Kinetics series looking at collision theory and the Maxwell-Boltzman distribution. So kinetics is the study of the rate of a reaction. And for a reaction to occur between two particles, they have to collide with enough energy to break the bonds, as well as the collision taking place between parts of the molecules that are going to react together. So not only the fact that the molecules have to have enough energy to break the bonds, they have to come together in the correct orientation for those bonds to actually have an effective collision and for them to be broken. Now, most collisions between molecules actually don't lead to a reaction. They either don't have enough energy or they're in the wrong orientation. Now, we can define the rate of reaction as being the change in concentration of a specified reactant or product per time. Now, it's normally easier to monitor the concentration of a reactant because we know typically how much we started with. We know the concentration that we will have started with. And so it's easy to kind of follow the fall in the concentration of a reactant or the rise in the concentration of a product. And so our rate of reaction is, well, how much does that concentration change in a given time? And there are several factors that affect the rate of a chemical reaction. So the first is increasing temperature. If we increase the temperature, this increases the average speed of the molecules. We've increased the energy that the molecules have. So essentially these molecules they've got more energy, they're moving around more quickly, and therefore the number of collisions that happens is also increased with increasing temperature. By giving them greater speeds, they can move around more and they're more likely to collide with each other. We can also increase the concentration. This is equivalent to putting more particles into a given volume. And so if we put more particles into the same volume, it means that collisions are more likely and the reaction rate would be faster. They're more likely to find each other and collide with each other. However, as a reaction proceeds, our reactants are used up and we form products. So as the reactants get used up, the concentration falls. And so typically a rate of reaction falls as the reaction proceeds. The rate of reaction isn't constant for a reaction. Typically it slows down as we go on because the reactants are being used up, and therefore collisions are less likely because they're further away from each other. The third is increasing pressure. So this has the same effect of increasing concentration in a condensed phase reaction. So essentially increasing concentration, which is taking part in solution, is the same thing as increasing pressure, which is for a gas phase reaction. There are more molecules in a given volume, and so collisions are more likely. Pressure can also be related to volume. Pressure is the inverse of volume. So increasing pressure is the same as decreasing the volume. It both leads to the same idea that we have essentially more molecules in a given volume, and therefore collisions are more likely, and so the rate will increase. We can also think about increasing surface area. So the greater the total surface area of a solid, the more of its particles are available to collide with other molecules. Essentially, rather than having one massive lump of something, we can break it down into lots and lots and lots and lots of little chunks. Well, now this has more particles essentially available to collide with other molecules. It increases the rate of reaction because there are more sites for a reaction. Essentially, we're increasing the chance of it being in the correct orientation to react. And the final one is using a catalyst. So a catalyst is a substance that accelerates the rate of a chemical reaction without being chemically changed itself. So the catalyst that you put in at the start of the reaction, you will regenerate at the end of the reaction. And it accelerates the rate of a chemical reaction because it provides an alternative route for the reaction to proceed down. And the key thing is that it has a lower activation energy, which we'll come to later on. So as we said previously, only a small number of collisions are actually successful and result in a chemical reaction. We said that for a collision to be successful, the molecules must have enough energy to start breaking bonds, and they must collide in the correct orientation. Now we can think about this energy bit a bit more. So the molecules must have a minimum energy enough to start breaking bonds, and this is called the activation energy, and it's given the symbol E subscript A. Now we can show activation energies if we draw a enthalpy versus extensive reaction diagram. So we'll have seen these diagrams if you've seen the thermodynamics videos on this channel. Typically, the y-axis is energy or enthalpy, the x-axis is the reaction coordinate, or sometimes called extent of reaction, sometimes called progress of reaction. Essentially, it just means how far along in the reaction we are, from reactants to products. And so we have the two examples here, an exothermic reaction and an endothermic reaction. Remember that in an exothermic reaction, we give heat out. So we have our delta H, our enthalpy change, being negative. So our reactants are higher up than our products. In an endothermic reaction, it's the other way around. We have heat being taken in, our enthalpy change is positive, and so we have our reactants being lower down than our products. Now we can think of activation energy essentially as being the hill, the size of the hill that we have to overcome before being able to come back down to the products. So while the enthalpy is shown as just a vertical arrow directly from the reactants to the products, our enthalpy, our activation energy has to be this kind of hill-shaped curve. And so we can't simply just go from reactants straight to products. We have to kind of sort of surmount this hill before we get down to our products. You can imagine that we have to kind of trying to roll a ball in the exothermic diagram there, trying to roll a ball up that side of that hill to go down. We'd have to give it some energy, enough energy to be able to reach the peak of that hill and then go down the other side. Now, a large activation energy means that a reaction will be very slow at room temperature, because if it has a very large activation energy, it needs a lot of energy to be able to have a successful collision. Well, at room temperature, very few of those molecules are going to have sufficient energy, so very few of those collisions are going to have the sufficient energy to be able to start breaking bonds. And so we can draw our activation energy curves on these diagrams. We always start from our reactants, end at the products, but the top point of this activation energy curve has to be higher than whatever the highest point already is. So for the exothermic situation, we have our reactants there, the highest point. So we start our curve at the reactants, we go slightly up, we reach our peak, and then we come down to the products. For the endothermic case, we start at our reactants, the highest point is the products, so our activation energy curve has to go slightly higher than this. And so we have our reactants going up slightly higher than the products, we have the peak, and then we come back down to the products. And you can see that I've labelled the activation energy with this green arrow. And so for our exothermic reaction, we have our activation energy going from the reactants to the top of that hill. And it's the same for the endothermic case. Our activation energy is always measured from the reactants to the top of the curve, and it's always positive. We have to put energy in to break bonds, remember. Now, the actual species that exists at the top of this curve, the thing that's in between reactants and products, is something called an activated complex. So this is where some bonds are in the process of being made, others have been broken, we're kind of halfway between our reactants and products. It's an incredibly unstable species. It doesn't exist as an intermediate, it's not, so we can't isolate it typically. And so we're sort of halfway between reactants and products. It's very, very unstable, as shown by the very, very high energy. You can see that the highest point of this is this activated complex. And so a key distinction here is that the actual species that exists is called the activated complex. The actual highest point on the energy curve, though, is called the transition state. So the actual energy is called the transition state. The species that exists, the activated complex. But the key thing, really, is that our activation energy is always positive, and it's measured from the reactants to the top of this curve. This then brings us on to something called the Maxwell-Boltzman distribution. And so the particles that we have in a gas or in a solution, they're all moving at different speeds. And the energy of the particle depends on its speed. And so the particles, because they have a range of speeds, they have a range of energies. You can imagine that some particles have a bit more energy than others, some have a bit less. Because they're colliding constantly, they're exchanging energy. So something that starts off with a lot of energy, collides with another molecule, then has a little bit less energy, slows down, collides with something else, gains some more energy. So all these energies are constantly changing, and it's a really, really wide range. Now, if you plot the energy against the fraction of particles that have that energy, we get something called a Maxwell-Boltzman distribution. And so our y-axis is the fraction or the number of particles that have a specific energy, and then the x-axis is the energy. Now, there's a few takeaway points from this. No particles have zero energy. Unless we're at 0 Kelvin, no particles are going to have zero energy. Even at room temperature, while they might not be moving particularly quickly, they're still going to have some energy. And so our curve starts from the origin point. It starts from exactly the intersection of the x and the y axes. Most particles have intermediate energies, and this is the peak of the curve. And I've labelled this here as the most probable energy. And so most particles, as you can see, that's the highest point, the y-axis being the fraction of particles with that energy. So that's saying that that's the energy that most particles have. And you can see that actually it's not particularly high up on the energy x-axis. Few particles have very, very high energies. And in fact, there's no upper limit. The curve actually doesn't ever reach the x-axis. It never collides back with the x-axis. It just kind of goes down to it but never reaches it. And so there's no upper limit to the energy that these particles can have. Now you also notice I've labelled another point on here called the average energy. And the average energy is not the same as the most probable energy. That's a really key distinction. Our most probable energy is the peak of the curve, i.e. the energy that most particles have. The average energy typically is a little bit further to the right of that. Then if we want to look at the area under the curve, essentially timesing the y and the x-axis together, well, we have the fraction of particles with energy E multiplied by energy E. And so the actual area under the curve is the number of particles. We can also label our activation energy. Remember that our activation energy is the minimum energy required for a successful collision, given the symbol EA. And so I've labelled that towards the right of the diagram. And so you can see that the minimum energy actually is quite high, and therefore not many particles have that minimum energy, hence why most collisions are unsuccessful. Now the area under the curve past the point EA, this is the point that I've kind of shaded in red, that is the number of particles that have energy greater or equal to the activation energy. And so because our activation energy is the minimum energy required to start breaking bonds for a successful collision, this is the number of particles essentially that partake in successful collisions. And again, you can see that that area, remember the area under the curve is the number of particles, the area under the curve past the EA point is quite small. So there's a very small number of molecules, very small number of particles that have that activation energy. And the need for activation energy to be present explains why not all exothermic reactions occur spontaneously at room temperature. If they did, that would be a bit awkward. We'd have sort of lots of things like petrol and stuff just spontaneously combusting. That wouldn't be fantastic, obviously. So the need for activation energy explains why not all exothermic reactions occur spontaneously, because not enough particles have this activation energy, even if it is an exothermic reaction. Now, the shape of this curve, the shape of the Maxwell-Boltzman distribution, changes with temperature. And we can imagine that that kind of makes sense, because as we change the temperature, we're going to be changing the distribution of speeds, and hence the distribution of energies within that sample. Now, at higher temperatures, the peak of the curve is slightly lower, and the peak moves to the right. And so what we're showing with this here essentially is that our most probable energy moves to a higher energy, so our peak shifts right. That makes sense. If we increase the temperature, particles will move faster, they'll have more energy. And the second is that because we've moved it further to the right, now more particles have the activation energy, either equal to the activation energy or greater than the activation energy. And so the peak, the most probable energy, is slightly lower down, because we now have more particles having energy greater than that. So the number of particles with very high energy increases. The key thing is that the total area under each curve is always the same, because no matter what the temperature we're at, the total number of particles never changes. We've not added more or taken away, we've just changed the temperature. So the area under the curve, which is the total number of particles, never changes. And so at higher temperatures, more molecules have energy greater than the activation energy, and so there's a higher percentage of collisions that will actually result in a reaction that will be successful. If we have more successful collisions, our reaction rate increases, and this is why reaction rate increases with temperature. Now we'll see in another video, when we look at something called the Arrhenius equation, that actually a pretty small change in temperature can produce a very, very large increase in the rate of reaction, and hence the number of particles that have energy greater than that activation energy. So we really don't have to change the temperature by very much to actually increase the rate of reaction by quite a lot. And so if we increase the temperature, the molecules tend to move faster, they now have more energy, and so the total number of collisions in a given time increases a little bit. However, this is not as important to the rate of reaction as the increase in the number of effective collisions, i.e. we have to have not only the particles moving a bit quicker, and so therefore they're colliding more, but it's the fact that more particles now have energy greater than the activation energy, and therefore they are effective collisions. If the energy didn't change, it doesn't matter if they're moving a bit quicker and colliding a bit more, because the energy hasn't changed and they're still therefore probably not going to have the activation energy. The key thing is that the number of molecules with the activation energy has increased. And another key takeaway is that higher temperature, higher speeds are more probable, and so therefore higher energies are more probable, and so therefore more particles have the activation energy. The area under the curve past the activation energy point increases. That then brings us on to catalysts. So we talked earlier that catalysts are substances that speed up the rate of a chemical reaction without being chemically changed themselves. And they're really important in industry because it's cheaper to use a catalyst to speed up a reaction rather than using high temperatures and pressures. By using high temperatures and pressures, we obviously have a much greater energy demand. That's quite costly. By using much higher temperatures and certainly higher pressures, typically we have to build special plants. We have to use special materials to withstand really high pressures and temperatures. There's also more safety implications in doing that. So it introduces a fair few issues. Whereas just using a catalyst, well, we don't have to use high temperatures, we don't have to use high pressures, we can just use the catalyst. And because the catalyst is chemically unchanged, we can then recycle the catalyst at the end and make it do another reaction. So it's cheaper to use a catalyst. And catalysts work by providing an alternative pathway for the reaction to proceed through, one that has a lower activation energy. And so they reduce the activation energy for a reaction. And therefore, obviously, if they reduce the activation energy, well, more particles now have energy greater or equal to that activation energy, and hence the number of successful collisions increases and the rate of reaction increases. And so we can show this either on an enthalpy diagram, or we can show this on our Maxwell-Boltzman distribution diagrams. So if we look at our enthalpy diagram, here I've shown an exothermic reaction again, the reactants being higher than the products. We can draw our activation energy on if we draw this kind of curve between the reactants and products, remembering that activation energy always goes up, it's always positive, and remembering that we always measure our activation energy from the reactants to the top of that curve. So the green line shows the reaction with no catalyst. The orange curve shows the reaction with a catalyst, and you can see that the activation energy, the point from the reactants to the top of that curve, is significantly smaller with the catalyst as opposed to without it. Sometimes as well, rather than a reaction that might take place in one step, using a catalyst might make the reaction happen in multiple steps. But the key thing is that if the activation energies are smaller than it was for the uncatalyzed reaction, then it will still be a quicker rate of reaction. It doesn't matter that we now potentially have 3 steps in our reaction rather than just 1 step. If the activation energies are smaller, the rate will be quicker because more molecules have energy greater than that activation energy, and therefore there are more successful collisions. If we show it on our Maxwell-Boltzman distribution diagram, we can essentially show our uncatalyzed activation energy in red. Our activation energy with the catalyst, we said it reduces the activation energy, so we draw our line to the left, lower energy, and then remember that the area under the curve represents the number of molecules. So the area under the curve past those points is the number of molecules or the number of particles that have energy greater than the activation energy. And you can see that for the no catalyst, it's just that red little region at the end. With the catalyst, it's not only the green region, but also the red region as well. So many more particles have energy greater than the activation energy, more successful collisions, more effective collisions, and therefore the reaction rate increases. A key thing is that catalysts do not affect the enthalpy change of reaction. They allow you to reach the reaction quicker, but they don't affect the overall thermodynamics of that process. So even in the, if we go back to our enthalpy diagram, looking at the green versus the orange line, while the activation energy arrows are different sizes, the enthalpy arrow, the red one, is exactly the same. The enthalpy change is unchanged by the catalyst. Nor does it affect the position of an equilibrium of a reversible reaction. So if you're not so happy with that idea, go to my equilibrium videos. But essentially the position of the equilibrium, the proportion of reactants and products that we end up with, isn't changed by a catalyst, because we have a forward reaction and a backward reaction happening at the same time, at the same rate. And so a catalyst affects both of those forward and backward reactions equally, and so there's no overall change. So catalysts are really, really important in lots and lots of industrial processes, again, because it's cheaper. Rather than using very, very high temperatures, high pressures, instead use a catalyst to increase the rate of reaction. And they're really, really widely used in industry. I've put this table in here just to show you the kind of scope of how these catalysts are used. And these are all reactions that you will either have seen before or you'll come across as you study your A-level chemistry. There's lots of examples here. There's the Haber process, which makes ammonia, incredibly important in terms of making fertilizers. And the catalyst for this actually is finely divided iron. There's the process for making nitric acid. This uses a platinum and rhodium catalyst. And nitric acid is also a fertilizer, but also explosives. We can see the hydrogenation of alkenes, so this hardening of fats with hydrogen. That typically uses a nickel catalyst, and the use of that is making margarine. When we crack our hydrocarbon chains from crude oil, we use an aluminium oxide and silicon dioxide as zeolite catalyst. That's very, very important for multiple reasons, but one of them being making petrol. There's also catalytic converters in car exhausts to convert these kind of toxic gases into non-toxic gases. That uses a platinum and rhodium catalyst, and so it gets rid of these toxic and polluting gases. There's the hydration of ethene to produce ethanol, a very, very important reaction. Ethanol is very, very useful, for the fuel. It's also used as a chemical feedstock. It's used as a solvent, as also well as going into alcoholic drinks. And so this typically is an acid catalyst, typically something like phosphoric acid. And then finally, an esterification reaction. This is making an ester from alcohol and carboxylic acid. And this has an acid catalyst as well, and that's very, very important for solvents as well. So there's a lot of uses of catalysts. So specifically, just looking at the catalytic converter for a moment, petrol engine cars are now equipped with catalytic converters in their exhaust systems. And these reduce the levels of a number of polluting gases. Now, the catalytic converter is a sort of solid catalyst. It's what we call a honeycomb. That's the sort of picture that we've shown there on the right at the bottom. It's made of a ceramic material that's coated with platinum and rhodium metals. They're the actual catalysts. And this honeycomb shape provides a really, really big surface area for the reactions to take place. And remember that we said that one way to increase the rate of reaction was to have a big surface area, because we have more sort of sites where we can have effective collisions. And so as these gases pass over the catalyst, they react with each other to form less harmful products. And so typically an example here would be to take carbon monoxide, that's a toxic polluting gas, and nitrogen monoxide. These react together to produce nitrogen and carbon dioxide, less harmful products. Another example would be if there's unburnt hydrocarbon. Well, this reacts with what we call NOx. These are nitrogen oxides. It could be NO, it could be NO2. This then produces nitrogen, carbon dioxide, and water, much less harmful products. And so the way this works is that we said our catalyst is essentially a solid support. So the gases, they pass over the catalyst, and the catalyst essentially provides a kind of solid support, a kind of place where this reaction can take place with a lower activation energy. So the gases pass over the catalyst and they form weak bonds with the metal atoms of the catalyst. And this is called adsorption. Now this holds the gases in just the right position and the orientation for them to react together on the surface. Remember that we said that the two things for essentially accelerating the rate of reaction was having the minimum number of energy, the activation energy, but also that they have to collide in the correct orientation. So what this catalyst does is allows them to be sort of held in a position where the orientation is exactly right for a successful reaction, as well as holding them in pretty close proximity, and so that's also going to increase the rate of reaction. So they react together on the surface, they form the products, and then the products break away from the metal atoms. This is a process called desorption. And this frees up room on the catalyst. Remember that the catalyst is unchanged in these processes, and so it frees up room on the surface for more gases to take their place and to react. Now the key thing is that we have to choose our metals very carefully, and there'll be a reason that we've chosen these platinum and rhodium metals, and the reason is because we have to have the right strength of bond. we have these weak bonds that hold the gases in place for them to react, and the strength of those bonds is really crucial. They must be strong enough to be able to hold the gases in place, but you don't want the bonds to be too strong that once the reaction has happened, the product can't be released. You wouldn't regenerate your catalyst and you wouldn't get your products out. Likewise, you don't want the bonds to be too weak because then it wouldn't actually hold the gases in place and allow them to react with a lower activation energy. So there's a real kind of Goldilocks effect here of something perfect just right in the middle. So, time to have a go at some questions. These are all to do with the kinetics that we've talked about. So have a go at the questions, pause the video if you'd like to, and the answers will be on the next slide. So the first question, I'm starting from the left-hand box. We have our gas phase reaction of hydrogen plus chlorine to HCl. And the first one was to define activation energy. Well, activation energy is the minimum energy required for a successful collision, and hence for a chemical reaction to occur. To give one reason why the reaction is very slow at room temperature, well, this is because most molecules do not have energy greater than the activation energy. So most of the collisions are ineffective. They're not enough to actually have a chemical reaction happen. Another way to say it would be that the collision frequency is very low because the particles don't have much energy at room temperature. They're not going to be moving particularly quickly, and therefore the collision frequency, how often they collide, is going to be pretty low because they don't have much energy. Part C was to explain why an increase in pressure increases the rate of the reaction. Well, an increase in pressure is equivalent to a reduction in volume. So we can think about having more particles in a given volume, more particles in a given space, and hence the collision frequency increases. Essentially, you can think of the particles now being closer together. They're more likely to see each other more often. They're more likely to collide more often. So the collision frequency increases, and hence there are therefore more successful collisions and therefore a faster rate of reaction. Part D is to explain why an increase in temperature, or a small increase in temperature, can lead to a large increase in the rate of reaction. Now, temperature is the average kinetic energy of the molecules. It's the total energy of the system divided by how much we have. And the key thing being that if we increase the temperature slightly, there are now many, many more particles with energy that are greater than the activation energy. Remember, a pretty small change in temperature can produce a huge change in the reaction rate because our activation energy, we have now more particles that have that activation energy. If you go back to your Maxwell-Boltzman distribution, remember that at higher temperature, the curve becomes slightly lower down and further to the right because more particles have energy greater than the activation energy, and therefore there are more successful collisions. Part E was to give the meaning of the term catalyst. So this is a species that speeds up the rate of a chemical reaction by providing an alternative route, one that has a lower activation energy, and therefore it speeds up the rate of reaction and it's chemically unchanged. And finally, part F was to suggest one reason why a solid catalyst is often in the form of a powder. Having it as a powder rather than just as a block of whatever the solid catalyst is increases the surface area, and this means there's more area, there's more sites for reactants to adsorb onto, and therefore more likely to have effective collisions. The second set of questions, the ones on the right, we have our Maxwell-Boltzman distribution curve that I've reproduced in red. The first was to label the diagram with the axes. So the y-axis is the number or the fraction of molecules with energy E. The x-axis is the energy. The second was to draw a curve for a lower temperature. So we said that at a higher temperature, the curve becomes slightly broader, goes to the right, and it becomes flatter. Well, the opposite is true for a lower temperature. The peak becomes slightly higher, and the peak becomes thinner. So this is the curve that I've shown in green. You can see our peak's higher up, and it's also further to the left on the energy axis. And what this is telling us is that essentially the most probable energy has fallen. That makes sense at lower temperature, that they're moving around less quickly, they have less energy, so the most probable energy is going to be lower. And also you can see that the curve as it goes towards the high energy size is much lower down than it was before. So remember that the area under the curve is the number of particles. And so if we have less area under that curve, less number of particles that have those higher energies. Part C was to say that in order for two particles to react, they must collide. Explain why most collisions do not result in a reaction. And there's two reasons for this. The first is that they either don't have the correct orientation, or, and quite often, they don't have the minimum number of energy. They have energy less than the activation energy, the minimum energy to start breaking bonds. D was to state one way in which the collision frequency between particles of a gas can be increased without changing the temperature. But if it's a gas, we can think about pressure, and if we want to increase the collision frequency, we increase the pressure because that's like putting more molecules into a given volume. Part E was to suggest why a small increase in temperature can lead to a large increase in the reaction rate. This is exactly the same answer as we had for 1D on the previous slide. And then F is to explain in general terms how a catalyst works, essentially just to define a catalyst. And so we say that a catalyst speeds up the rate of a chemical reaction without being chemically changed itself, and it provides an alternative pathway for the reaction to proceed down, one that has a lower activation energy and therefore allows for a faster rate of reaction, because more collisions are therefore successful and effective. So thank you for watching this video. You can find more videos like this on my YouTube channel. If you found this video helpful, please consider leaving a review on my tuition website. I also offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.